This is the ME452 final presentation for analysis and redesign of cooking scales with team members Angelica, Eric, Clayton, Leo, Nina, and Akil. Our proposal is to redesign a cooking scale. Here's an assembled view along with an exploded view. Our production volume is 100K units and the market size is 613 million. Here's a drawing of the assembled view. Here's a drawing of the exploded view and a relevant bill of materials.
The primary customers of a kitchen scale mainly include professional and at-home chefs and bakers who use the kitchen scale as one of the main methods for ingredient measurement in their food-related work. The secondary customers of a kitchen scale include fitness influencers, bodybuilders, culinary teachers, and researchers, all who use the scale to measure for their own needs. This fast diagram describes the functions that the kitchen scale must perform. We have two primal basic functions, weigh food and take measurements. These work with the supporting functions to contribute to the main task function of quantify food.
This is the function component mapping matrix where the columns are the functions and the rows are the components of the scale.
Here's our quad chart to assist us when we redesign for manufacturing and assembly.
Considering the target customers, we developed the functional differentiation table shown on the left. We determined that basic functions like display numbers would be identical between customer groups, but supporting functions like stop display would be different. Taking these ideas, we developed the component commonality table shown on the right.
This then translates into the component commonality table, where you can see most of the parts are the same across platforms, but there are only the upper parts that separate the modules, as can be seen in this slide, where you can see the original circular flat pattern, and then also the bowl module that is for small loose objects, and the square module, which is better for supporting larger prismatic objects. They have a common interface in that they all attach to the weighing support.
And now I want to talk about the feasible assembly process. Starting with the top-down approach from the plugs to the battery cover proved to be less efficient, given the assembly process differentiated once a platter is inserted, since there are different shapes for each variant. The improved assembly process starts from the bottom with the batteries and ends with the plug securing everything in place, allowing for delayed differentiation in the assembly process. Edited from the interim report, callouts have been included to showcase the major changes from the top-down assembly process to the bottom-up assembly process.
We first conducted design for manual assembly analysis for the original scale design to obtain the assembly times shown in this table. Observing these times while considering the mentioned quad chart and function component mapping matrix, we chose the circuit board as a platform component with its high cost and high importance, and considering the high assembly time of the circuit board screws. We further chose the translucent top as a modular part because of the relatively high cost and assembly time of the button pins, which are part of the translucent top. We redesigned these parts using design for assembly guidelines indicated here, reducing fasteners, providing locating features, and applying Z-axis assembly. This had minimal impact on the product function, but presented some influence with the manufacturing cost because of material manipulation. In performing the analysis with our new design, we observed significant change in the total assembly time required for the translucent top, which reduced total assembly time by about 40 seconds and improved assembly efficiency by about 5%.
In our redesign for automated assembly, we decided to analyze the scale base, sensor, and sensor bracket subassembly due to the quad chart for DfM. We modified 3 features as seen on the slide, 2 modifications being based on guideline DFA-10, and the third feature being based on guideline DFA-7. The first 2 modifications help with the insertion of the scale sensor and the fasteners for the scale sensor bracket. The third modification added a slot to the sensor to change its silhouette to be asymmetrical, helping with orientation in an automatic feeder, along with aiding in alignment and insertion. We then analyzed the effect that the redesign had on the functionality and the assembly cost of the subassembly. We found that the function of the assembly was not altered due to the redesign of these parts, and the assembly cost went down by 12%, as seen in the table on the slide. The decrease in cost came from the scale sensor and sensor bracket fasteners.
Based on the function component mapping matrix, we know that the scale base needs to support weight and ease removal. As part of the ease removal requirement, the distance between the battery tabs led to a tolerance choice of 0.1 millimeters, as this range ensured contact with the battery while preventing too much spring compression for easy removal. The spacing for the scale bracket mounting holes was also key for fulfilling the scale base's support weight function. The scale sensor needs to ensure accuracy and support weight based on the function component mapping matrix, and a tolerance level of 0.1 millimeters was chosen as this level ensures the fasteners will align and for the part to have consistent bending characteristics, which will meet these 2 needs. The final recommendation is to use machining for the scale sensor and injection molding for the scale base. This is based on material, shape, mass, maximum section thickness, tolerances required as found previously, economic batch size, and surface roughness.
Here's the weighing sensor beam that we choose to redesign. Using the analytical method and assuming 100K units of production volume, the total cost per part is estimated to be $9.077, and the cost breakdown is shown in the table below. The only recommendation given by DfM Pro is to change the diameter of the through hole into standard sizes, because unusual sizes require special tools and will result in additional costs. Based on the recommendation of DfM Pro, we will change the size of the through hole to 4.3 millimeters, which is also the standard size for an M4 screw clearance hole. In addition, we will change the blind hole on the bottom side into a through hole. We will also change the size of all the holes to be 4.3 millimeters. With these changes, we will save the time to flip the part and change the drill bits. Using the analytical method, the total cost per part is estimated to be 8.046, with the breakdown shown in the table. We quoted from hubs for volumes up to 1,000 units and extrapolated the data to 100K units. The comparison between the before and after design is shown in the second table, and we can see the percentages of cost reduction.
Designing for the manufacturing with the injection molded part led to a cost of $1.90 per part. When using DfM Pro, we chose the suggestions minimum radius at base of boss, minimum radius at tip of boss, and undercut detection. The minimum radius parameter asks us to use smooth contours and to fillet edges of cylindrical features at the top and bottom of the base. The undercut detection parameter asks us to avoid or replace undercut features that require a core lifter to remove. To address the minimum radius parameter, we added fillets for the posts on the top, as well as rounded feet on the bottom. To address the undercut avoidance parameter, we reduced to one attachment point for the battery case, removed the other undercut, and extended extrusion through the part. This reduces the core lifters from 2 to 1 and replaces one with a side pole. This positively affects our mold costs due to the expense of core lifters, which ultimately reduce our cost to $1.86 per part, which is a 4-cent difference per part. The changes do not affect the functionality of the part.
In order to maximize our product's use to consumers, we will incorporate a mobile recipe and nutrition management software that tracks calories, generates recipes, creates a market space for secondhand users, and measures nutritional value based on the foods that are measured on the scale. This will improve consumer experiences by removing the need for manual calculations and disproportionate recipes. Additionally, it promotes sustainability by extending the product's life cycle, encouraging practices such as reducing, reusing, and recycling, as well as facilitating appliance trading to minimize overall waste.
In conclusion, $7,000 was saved in total production costs due to design for assembly, and $103,000 was saved due to design for manufacturing. We also learned many lessons and believe that there may be opportunities for more DFA and DFM. Possible improvements include using more standard parts to save on cost, such as using an off-the-shelf load cell beam, as our cost savings in assembly could be offset by losses due to not being able to compete with current manufacturers' economies of scale. Lastly, some modifications may affect the function of parts in ways that we cannot verify without direct testing, so this is another way we could potentially improve.